All these four properties are related to estimate. What's meant by unbiased? Unbiased is referring to beta hat, meaning that whereas estimates are unbiased, whereas estimates are linear. Okay, the word linear here is not referring to equation or regression equation. It is linear that relates to ONS estimator, as well as efficiency, or minimum variance of ONS estimator, and consistent. And now, if you refer to page 124 to 125, here about Gauss-Markov theorem. Okay, this theorem proves two important properties of OS estimators. Okay, actually it is not two, it is three. Okay, this theorem is proven in all advanced econometrics textbooks, but for a regression user, it's more important to know what the theorem implies than to be able to prove it. Okay, we are not going to discuss how to prove all the properties, okay, either biased, linear, efficient, and consistent. We just want to know what is the implication, okay, when we have unbiased, linear, and so on. So the Gauss-Markov theorem states that given classical assumption 1 through 6 that we discussed before, okay, 1 through 6, starting from regression model is linear, no explanatory variable is perfect linear function of any other explanatory variables, the no correlation between the error terms, okay, the variance of the error term must be constant, and so on. So considering classical assumption 1 to 6, the ordinary least squares estimator of beta k, meaning that the symbol here is beta hat k, because we have to take the phrase here estimator of the true beta, meaning that the estimated beta is the minimum variance of estimator from among the set of all linear unbiased estimators. Okay, based on Gauss-Markov, okay, the properties of OS estimators are unbiased, okay, minimum variance, and also set of all linear. So linear. Okay, in other words, based on Gauss-Markov theorem, The OLS properties are unbiased, linear, and minimum variance or efficient. Condition that all of them, the OLS estimators, fulfill assumption number 1 to number 6. What is assumption number 1? Up to 6. Okay, regression model is linear. The error term has zero population mean. Okay. No perfect correlation. No correlation between independent variables and the error term. Okay. No correlation between variables. Sorry, between the error terms. 4. And 5. Constant variance of the error term. No heteroscedasticity. Case 6, no explanatory variable is a perfect linear function of any explanatory variables, meaning that no perfect multi-collinearity. And excluded assumption 7. Okay, by satisfying all the 6 assumptions, 1, 2, 3, 4, 5, 6, okay, the regression equations will have linear estimators, unbiased estimators, and also minimum variant estimators. Okay, next is based on Gauss-Markov theorem. The theorem says that all S properties for estimators are unbiased, linear, and minimum variance. Or efficient, or known as best. So these 3 properties can be summarized in one word, known as blue properties. What is B? B referring to best, minimum variance. L is linear, and U is unbiased, E is estimators. So blue is referring to best or efficient minimum variance of all S estimates, linear and unbiased estimators. Okay, in other words, based on Gauss-Markov, there are 3 properties. First is linear estimator, unbiased estimator, and efficient all S estimator or estimates. Okay, if we refer all the 7 classical assumptions, all S estimator can be shown to have the following properties. Okay, by including other assumptions, 7, okay, we will have the number of properties here is 4. Okay, unbiased, linear, then minimum variance or efficient or best, and lastly consistent. Okay, consistent. So we go one by one, unbiased. Okay, first is unbiased. And in the book, it starts with they. If in your test or your exam, you put they are unbiased, okay, I'll give you 0 because I do not know what is meant by they. Yeah. They is referring to what? I do not know. Okay, because in the book, okay, we have okay, the statement here, known as coefficient estimators. So they here is referring to estimators. So it is clear in the book. But when it comes to you answer the question, you start with they, okay, without any statement before. So I assume I don't know what is meant by they. So you must know how to tackle when it comes to test or exam in giving a clear statement, a clear answer of the question. So here estimators are unbiased. What is meant by unbiased here? That is the estimated beta hat is equal to its true value. This is true value. True value of beta hat. This means that the OLS estimates, okay, estimators are the same, referring to beta hat. Of the coefficients are centered around the true population values of the parameters being estimated. So what is meant by this statement? It is easier if we illustrate using a diagram. Okay, the horizontal axis is beta hat, not beta. Okay, the center value is expected value of beta hat, and also is equal its true value. So in this case, beta hat is unbiased. Okay, OLS estimates are unbiased. Okay, why? Because the estimated coefficient or OLS estimates on average, it is equal to its true value. Is equal to its true value. Okay, next another example. Okay, the value of beta, the true value, is not equal to expected value of beta hat, or here. So in this case, expected value of beta hat is not equal to its true value. So beta hat here is biased. It is biased. Okay, then the second properties. Okay, the second property of OLS estimate is minimum variance. Again, D here is referring to estimate. Okay, OLS estimate is minimum variance. Okay, what is meant by minimum variance? The distribution of the coefficients estimates around the true parameter values is a tightly or narrowly distributed, as is possible for n unbiased distribution. Meaning that the OLS estimate with small variance, okay, as is possible, is considered as minimum variance. No other unbiased estimator has a lower variance for each estimate than OLS. Okay, let's say beta 1 OLS, we have other coefficient estimated by GLS, okay, other estimated coefficient, okay, estimated by WLS, and the variance here, let's say I give the numerical example, it is 2, it is 4, it is 10. So the lowest is beta hat with OLS. So this is considered as, okay, beta hat has a minimum variance. Okay, therefore beta hat is efficient or best. Okay, let's say we have two estimators. Okay, this is the distribution of beta hat of beta hat, and we have another distribution of another estimate let's say beta hat star is equal to its true value. This is the distribution of beta hat star. So which one is efficient between beta hat star and beta hat? Okay, which one is efficient? Definitely beta hat star. Okay, why? Because of this estimator has the lowest or minimum variance. Okay, both are unbiased. You can see that the expected value of beta hat is equal to its true value. Here, the expected value of beta hat, okay, is equal to its true value. Okay, both are unbiased estimators, but in terms of efficiency, beta hat star is more efficient compared to beta hat because it possesses the smallest variance or minimum variance. Therefore, beta hat star is considered as efficient estimator. So this is minimum variance or efficient or best. Okay, the third property is linear estimator. Or they are linear. It is linear. Okay, what is meant by this third property? The OLS estimator is a linear function of a random variable. Okay, the OLS estimator is a linear function of a random variable. In this case, dependent variable. For example, here regression model y is equal to beta 0 at plus beta 1x plus d error term. K error term is random or stochastic. And we discussed in our earlier lecture, this is deterministic component. Okay, what is meant by beta hat is linear? Okay, in this case, beta hat 1, K is, if you recall how to compute beta hat 1 here, is the sum x minus x bar times y minus y bar divided by the sum x minus x bar squared. So this term x minus x bar is the small x, y minus y bar is the small y. So it can be written as the sum of xy divided by the sum of x squared. Or I can write it as the sum of x over the sum of x squared times y. or it can be written as beta hat 1 is a function of y. What is y is a random variable. Okay. The dependent variable which is random. So if beta hat 1 here is positively related, meaning that as y increases, the value of beta hat 1 will also increase. If it is negatively related and increase in a random variable, it will decrease the value of beta hat. What is beta hat? Is the slope. Okay, the slope becomes less steeper. Here, the slope becomes more steeper. Okay, that is number 3, third property of OLS estimator. Okay, then the last one is consistent. Okay, the fourth property is OLS estimators are consistent. Okay, they are consistent, meaning that estimators are consistent, and it refers to a large sample property. In this case, as the sample size approaches infinity, meaning that the size is large enough. When you learn the properties of OLS, okay, we need large number of sample size. So make sure that when you do an investigation, your sample size must be large, not 10, not 15, not 20. Okay, if the observations you can get 100, okay, you go for 80 or 90 or more. Okay, mass approaches infinity, meaning that as the sample size, okay, approaches population, the estimates converge to the true population parameters. As the sample size close to um, if you have large enough of sample size, okay, your estimated coefficient, okay, will close to its true coefficient. So our task here, when it comes to econometrics, we want to have our estimation must be precise or precisely estimated. So one way to have highly precision of your estimation results is to make sure that your n is large enough. Okay, is large enough. If in your first degree your advisor saying that okay 10 is enough, 15, as long as the results okay can be produced, okay, you okay can throw this kind of idea into the dustbin. Okay, refer to the econometrics book. Okay, it states that we must have large sample size. Only then we can achieve efficiency, okay, in our estimation result. Put differently, as the sample size gets larger, the variance gets smaller. Okay, as sample size gets larger, the variance of beta hat okay, tend to be smaller. Therefore, each estimate approaches the true value of the coefficient being estimated. Okay, therefore, the estimated coefficient would be close to its true value of the estimated coefficient. This is the advantage to have large number of sample size. This is the reasons if you don't have okay large enough of sample size, you cannot proceed with regression analysis. You can have the results, but the results are not reliable. So again, if we do not refer to Gauss-Markov theorem, the properties of OLS estimates are four. Okay, unbiased, linear, minimal variance, and consistent. If we refer to Gauss-Markov, the properties are three, which is blue. It's known as blue properties, best linear unbiased estimators. Okay, now we go to the new topic, okay, dummy variable. Okay, page 221 to 223. Okay, I give you 3 minutes to read. Okay, page 221 to 223. Okay, dummy variable. Okay, the dummy variable here can be intercept dummy, or it can be slope dummy. Before this, okay, we are exposed to the regression equation y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 and so on, plus the error. So what is the value of x's here? They are all assumed quantitative independent variables. Okay, quantitative independent variables are nominal scale variables. Okay, for example, income, output, sales, inflation, GDP, economic growth. They are all ratio scale variables. And now we will introduce the dummy variable. So we include dummy variable as one of the independent variables. We include here as one of the independent variables. If you go to high level of econometrics, we can also include our dummy variable as the dependent variable. So the estimation would be totally different. It is no longer OLS, but we are dealing with logit, probit, and tobit. So when it comes to dummy variable, we just limit our discussion. The dummy variable is introduced as one of the independent variables. So based on the book page 221, okay, we introduce the concept of a dummy variable, which we define as one that takes on the value of 0 or 1. So the value of a dummy variable, there are two values, 0, either 0 or 1. It cannot be 2, it can be 4, and so on. The value fixed either 0 or 1, depending on a qualitative attribute such as gender, okay, race, citizenship, and so on. In that section, our sole focus was on the use of a dummy variable as an intercept dummy. So what is intercept dummy? When we introduce dummy variable as one of the independent variables. Okay, as given in equation 7.16 here. Okay, variable D is introduced as one of the independent variable instead of X. Okay, instead of X. So D here, 1 if the ith observation meets a particular condition, 0 otherwise. Let's say the dummy variable is gender. Okay, 1 referring to male, 0 otherwise, meaning that it is referring to female. Or we can define 1, we give the value of 1 for female and 0 for male. It has no problem. Okay, that is intercept dummy. It is known as intercept dummy variable. Why it is known as intercept dummy variable? Because this variable will change the value of intercept. It will give an impact on the value of intercept. That's why it is known as intercept dummy variable. When we introduce dummy variable as one of the independent variables. Okay, next is slope dummy variable. Okay, what is slope dummy variable? The variable that is introduced as an interaction between a dummy variable and quantitative independent variable. Interaction. What is meant by interaction? Meaning that we multiply a dummy variable and a quantitative independent variable. Okay, slope dummy. Okay, the most frequent application of interaction terms involve one quantitative variable, and one dummy variable. We multiply x and d1. x1, d1 is known as a slope dummy variable. Okay, slope dummy variables allow the slope of the relationship between the dependent variable and an independent variable to be different depending on whether the condition specified by a dummy variable is met. Meaning that when we introduce slope dummy variable, the slope of that particular quantitative independent variable will change. In other words, it will change, okay, the value of slope coefficient. That is why it is known as slope dummy variable. And the example of slope dummy variable as given in equation 7.7 here, this one, x times d, or it is known as interaction between x, a quantitative independent variable, and a dummy variable. Or we can write as xd or dx. Okay, that's no problem. Okay, for example, here gender, we have two categories, male and female. We can give either the value 0 for male, okay, or 1 for female. Or we can give the value 1 for male, 0 for female. So in a regression equation or regression model, we have dependent variable, we have independent variables. So independent variables can be 100% quantitative independent variables, can be a mixture of quantitative independent variable and qualitative or dummy variables. Dummy variable sometimes is known as categorical variable. Okay? Categorical variable that we can categorize, okay, groups when we introduce dummy variable. Okay, the question here, how to assign the value of 0 and 1? It depends on a researcher. Okay. Use the same example, gender, that's two categories. Okay, we can assign 1 for male, 0 for female, or 0 for male and 1 for female. And how many dummy variables should be introduced? How many dummy variables should be introduced? So we have the rule, if a dummy variable has two categories, therefore only one dummy variable should be created, should be introduced, only one. If we have two categories. Or in a general, we can make it generalized. If we have n categories of a dummy variable, so we should introduce n-1 dummy variables. For example, when it comes to race in this country, we have Lay or Bumi, Chinese, Indian, and others. Okay, Lay or Bumi, Chinese, Indian, or others. There are 4 categories here in your questionnaire. So how many variables of race should be introduced? It should be 3 dummies, 3 dummy variables or 3 dummies. So in this case, our regression equation here y is equal to beta 1 plus beta 2x. X is a quantitative independent variable. Alpha m. M is our first category, Lay or Bumi. Plus alpha 2c is the second category, Chinese. And alpha 3 I is the variable that represent the group of Indian. And others, okay, won't appear in this regression equation. If we include others in this regression equation, we might have, okay, a big problem. Okay, extremely big. So what is N, what is C, what is I? We define that N, okay, C and I, there are 2 values, 1 or 0. So for variable N, if a person is Malay, so we give the value 1. If the person is other races, other than Malay, we will give the value 0. Okay, and for variable C, the value of 1 is meant for Chinese, other than Chinese would be the value of 0 for variable C. For variable I, 1 is meant for Indian, other than Indian it is 0. Okay, you can copy this equation and the example here if you want to. I give you 3 minutes. So in your data set, you have dependent variable y, as in this equation y, we have the quantitative independent variable x, x, and the dummy variables m, c, and I. So let's say our respondent here, you distribute the questionnaire and the respondent will answer your questionnaire, and the respondent is Lee. So the value of y for that particular respondent is 8, y is 10, x is 8. Because of the person, the respondent is Lee, for variable n, dummy variable n, Malay will fall under this category, the value of 1. So for variable Malay here in your data set, it is 1. Then how about variable C? Malay will fall the category of otherwise. So the value is 0. So this is 0. And for variable I, Malay will fall under otherwise. So the value is 0. Chinese, variable n, it falls under otherwise. So this is 0. For variable C, Chinese okay, will be assigned with 1 because it falls under the category of Chinese. So this is 1. Okay, for variable I, Chinese will fall under otherwise. So 0. Then Indian, okay, the same thing. For variable M falls under otherwise 0. For variable C falls under otherwise 0. And for variable I, it falls under the category of Indian, so 1. So next is, let's say, okay, Portuguese. Okay, Portuguese. Okay, Portuguese will fall under otherwise 0. Okay, Portuguese will fall under otherwise. For C, it is 0. For variable I, Portuguese will fall under otherwise 0. So for other races, okay, the values of the dummy variables are all 0. That is why we need 3 dummies, not 4 dummies. So I can summarize what is the dummy variable. It is the indicator variable or categorical variable. Is an artificial variable created to represent an attribute with 2 or more distinct categories or levels. So example for dummy variable here can be gender, can be race, can be weather, can be economic crisis. Okay, because of gender has 2 categories, we will introduce 1 dummy. In this case, race, we have 3 categories: Malay, Indian, and others. We introduce 2 dummies. Weather, good and bad. Okay, 2 categories. We introduce only 1 dummy. Economic crisis, there are 2 categories: pre-recession and post-recession. We introduce 1 dummy. Okay, the formula is n minus 1, where n is the number of categories. Okay, next is the concept of ANOVA and ANCOVA. We go to the first one, okay, ANOVA. Okay, I give you 2 minutes, okay, to copy. Okay, ANOVA model is a regression model okay, that contains independent variables that are all exclusively dummy or qualitative in nature. So when we have the regression equation where the independent variables are all dummy or qualitative variables, that particular regression equation is known as ANOVA model. So the regression equation here, the dependent variable is quantitative dependent variable, but when it comes to independent variables, variable G, variable N are dummy. They are dummy. There is no quantitative independent variable. Therefore, this regression model is known as ANOVA model. So in this case, gender, we have two categories. We just introduced, okay, one dummy. Okay, so we have only one dummy variable for gender. And the nationality, we have two categories, okay, Bangladeshi and Indonesian. So we introduce one dummy variable for nationality. In this equation, all the independent variables are dummies, or qualitative, or categorical, or indicator variables. Okay, next is ANCOVA. Okay, I give you 1 minute to copy. Okay, next is ANCOVA. What is ANCOVA? It's a regression model that includes both quantitative and qualitative variables as independent variables. So in our regression model here, we have a mixture of quantitative, independent variable, which is x, and we have qualitative independent variable. It can be intercept dummy or slope dummy, or both, either intercept or slope dummy, or both. As long as we have qualitative independent variable and quantitative independent variable, so this model is known as ANCOVA model. And in this case, we define that 1 is variable of gender, D1, variable of gender, male versus female. D2 is nationality of a worker, either from Bangladesh or Indonesia. And X is the quantitative independent variable that measures the number of man hours. Y is also quantitative variable. Okay, it is monthly salary. Okay, next we go to interpretation. Okay, example. Interpretation of intercept dummy. Okay, y is equal to beta 0, beta 1, beta 3. Okay, D1 is gender, 0 and 1. Let's say 1 is male and 0 is female. Then X is the number of man hour. and Y is monthly salary. Okay, interpretation of coefficient D1. Okay, how to interpret coefficient X? Okay, beta 3 here. You can refer what we have discussed, okay, before. So what is beta 1 here? Beta 1, we differentiate Y with respect to D1. And remember that D1 here, we have two categories, 1 and 0. What is meant by 1 is the group of male worker. And here is female. When we write beta 1, automatically it is understood that the sign here is positive. And it is over the value of 1 and plus. Okay, when it comes to interpretation for a dummy variable, the slope or the coefficient of a dummy variable, it is no such thing as 1 unit increase in D1. Okay, it is meaningless. Okay, it doesn't make any sense. Okay, by mentioning 1 unit increase. If you mention 1 unit increase, is it you are referring to 0 to 1? If yes, meaning that female turns to be male. So it sounds weird. That is why interpretation when it comes to dummy variable is totally different as quantitative slope coefficient of quantitative independent variable. So here we start with y, the dependent variable. We can say that what is y? The monthly salary. Okay, the monthly salary then followed by category 1. Okay, 1 here. Followed by category 1. Monthly salary of a male worker. After that, the value of slope coefficient here, beta 1, is beta 1. What is meant by positive? Higher. Higher. Then followed by a category of 0. Higher than a female worker. So the full sentence, the monthly salary of a male worker is beta 1 higher. Higher due to positive sign of the slope coefficient than a female worker. We compare 1 and 0 categories. Male and female worker. This is how we interpret the slope coefficient of a dummy variable. Any question? Okay, if there is no question, then we go to three possibilities of introducing a dummy variable. First, we can have differential intercept coefficients, but the same slope coefficient. We can have differential slope coefficients, but the same intercept coefficients. Third, differential slope coefficient, as well as intercept coefficients. Meaning that both are different, slope and intercept. Okay, we go to the first one. Okay, differential intercept coefficients, but the same slope coefficient, meaning that the slope coefficient is unchanged. We can have this by introducing an intercept dummy variable as one of the independent variables. Okay, for example, y is equal to beta 0 plus beta 1 d plus beta 3. Beta x and the other. So what is meant by intercept dummy here? Intercept dummy variable is this variable d. We introduce variable d as one of the independent variables. Our IVs, we have d and x independent variables. Okay, using the same example, okay, y is monthly salary. Okay, d we have 1 is male, 0 meant for female. Because of variable d, dummy variable here has two categories. So there are two individual estimated regression equations can be constructed. It can be constructed. So when we estimate this equation, the estimated equation can be written as y hat is equal to beta 0 plus beta 1 hat d plus beta hat 3 x. Or we can write here as expected value of y is equal to. Okay, from here we can construct two individual estimated regression, specifically for male and for female, by substituting the value of d. If d is equal to 1, meaning that we are referring to a male worker, so y hat here, monthly salary for male, subscript male, or we can write as expected value of y slash, it is not over, it is slash, d is equal to 1, the value of 1, then equal don't forget to close the bracket, then write equal beta hat 0 plus beta hat 1 plus beta hat 3 x. And here you substitute with value 1 for variable d.
Doctor,
Any problem?
in the equation there is no beta hat 2. Is it because the variable consists of male and female?
Again?
In the equation there is no beta hat 2. Is it?
That's the beta hat 2.
Yes, is it because the d variable consists of male and female?
No, we just assume in this equation we have two variables, one is d, one is x. Okay, you can put here instead of beta hat 3, beta 1000. It has no problem.
Okay.
Okay?
Thank you, okay.
Alright. So this is beta hat 0 plus beta hat 1 plus beta hat 3 x. So here is the value of intercept. Okay, intercept for male worker. That's why we say that intercept dummy variable will influence or will affect the value of intercept. Okay, next, what happens if D is equal to 0, referring to female? Okay, Y hat for female is equal to expected value that Y slash the value of D is equal to 0. Don't forget to close the bracket, and equals to beta hat 0 plus beta hat 1 beta hat 3 x. In this bracket, we'll replace D with the value of 0, referring to female. This is beta hat 0. Beta hat 1 times 0 is 0. Beta hat 3 x. You can see here the intercept is beta hat 0. Different category of workers, different gender of workers, okay, you can have different intercept. This is the value of intercept. Okay, intervals are different. Okay, but the slope, the slope for male and female, are the same, which is beta 3. That is why when we introduce the intercept dummy, we will have differential intercept, differential intercept coefficients, but the same slope coefficient. This is one of the possibilities. And these two regression equations we can illustrate in one diagram. Okay, remember that the vertical axis here is the value of dependent variable y, and horizontal axis is the value of quantitative independent variable x. It is not D. How come you plot y versus the categorical variable? And if you refer to this equation, these two, there is no variable D. Variable D is disappeared once we substitute the specific value of D. Okay, so for monthly salary, for males monthly salary, the intercept is beta hat 0 and beta hat 1. So we assume, assume that beta hat 0, beta hat 1, beta hat 3 are positive. So if they are all positive, beta hat 0 plus beta hat 1 must be higher than or greater than beta hat 0. When we want to construct a regression line for male, the value of, let's say the value of beta hat 0 plus beta hat 1 is here. This is the value of beta hat 0 plus beta hat 1. So this equation is y hat for male is equal to beta hat 0 plus beta hat 1 plus beta hat 3 x. And this is the intercept. The slope is beta hat 3. For female, the intercept is beta hat 0, which is lower than beta hat 0 plus beta hat 1. Let's see here. The slope for both are the same. The implication of the same slope can be shown. These two regression lines must be parallel to each other. So the slope here is beta hat 3. Beta hat 0. So this is y hat for female is equal to beta hat 0 plus beta hat 1 x. Okay, the intercept here for female is beta hat 0. For male, beta hat 0 plus beta hat 1. Both are different. Here, differential intercept coefficients, but the slope, okay, the slope for both are the same. This is, okay, first possibility. How to get, okay, the intercept is different and the slope, okay, is the same when we introduce and intercept dummy variable as one of the independent variables.
Doctor,
Yes,
for the female one, is it beta hat 1x or beta hat 3x?
beta hat 1x. Where is beta hat 1?
For the line,
For the line. Oh yeah, correct. This one. Okay, I get it. This is beta hat 3. This is beta hat 3. Beta hat 3, right? Okay. Okay. Okay, next is differential slope coefficients but the same intercept. Okay, differential slope coefficients but the same intercept. Okay, we will get slope differential and the same intercept. Okay, when we introduce slope dummy variable. Okay, by introducing a slope dummy variable in a regression equation. Okay, example here. Y is equal to beta 1 plus beta 2 plus beta 3 x plus the other plus beta 2 beta 2 x d or dx. You can write as xd or dx. So this is the slope dummy variable. Or it is known as interaction term. Okay, between a quantitative independent variable and a dummy variable. So in our data set, y x d y x d y x d. Okay, y x d and interaction term x times d. Okay, let's say your respondent here, okay, female, male, female. Okay, your quantitative variable, the values for y, let's say 0, 4, 20, and x 4.9, 21.5, and 2.6. And your d, how do we define d? What is 1? 1 is male, 0 is female. D 1 is male, 0 is otherwise, other than male, meaning that female. So if the respondent is female, the value is 0. The respondent is male, the value is 1. Okay, the respondent is female, the value is 0. So the interaction term can be created by multiplying x times d. Okay, x times d is 0. 4.1 times 0, it is 0. 21.5 times 1, it is 21.5. 2.6 times 0, it is 0. This is how we generate, okay, the value of interaction term or slope dummy variables. So when we estimate estimated regression equation, it becomes y hat is equal to expected value of y is equal to beta hat previously I used beta hat 0. Okay, I'll change it to beta 0 here. Okay, beta hat 0 plus beta hat 2 x d plus beta hat 3 x. Okay, because of the dummy variable here, we have two categories. We can construct two individual estimated regression equation. So if d is equal to 1, meaning that male, so y hat for male is equal to expected value y, given that d is 1, so beta hat 0 plus beta hat 2 x plus beta hat 3 x. Okay, variable d here will be replaced by 1 because it is male. Okay, what we get here, beta hat 0 plus beta 2, x times 1, it is x, plus beta hat 3 x. Beta hat 0, we have the same variable here, we can factorize. Here we take out x, beta hat 2 plus beta hat 3 x. Now you can see that the slope coefficient for male worker is beta hat 2 plus beta hat 3. Okay, next, if D is equal to 0, here referring to female, okay, Y hat for female worker is equal to expected value of Y, okay, slash D is equal to 0 is equal to beta hat 0 plus beta hat 2 x plus beta hat 3 x. So the value of D is 0. So that the equation becomes beta hat 0, beta hat 2 times x times 0. So this term is 0 or disappeared from the equation. Okay, plus beta hat 3 x. And you can see the slope coefficient for female is beta hat 3, which is different with the slope for male worker. And how about the intercept? The intercept here remains unchanged at beta hat 0. And we can construct these two regression lines, okay, on the same diagram. So make sure that you label the correct axis. Okay, if you label the axis, although the diagram, okay, the lines with all the values are correct, it is considered as strong. Okay, Y and X. Both must be quantitative variables. Okay, we construct for male. The intercept is beta hat 0. Beta hat 0. and the slope here beta hat 2 plus beta hat 3, and this is the regression for y hat mil is equal to beta hat 0 plus beta hat 2 plus beta hat 3 x. Okay, then for female, the slope is beta 3, beta hat 3. It implies that the slope for female must be more flattened or less steeper than the slope for male worker. So the slope here is beta hat 3. Y for female is equal to beta hat 0 plus beta hat 3 x. Both regression lines starts at the same value on the vertical axis at beta hat 0. It means that these two regressions have the same intercept, but the regression lines for these two, okay, are not parallel, okay, which means the slope for both are different. So this is the second possibilities. Okay, differential slope coefficient, but the same intercept coefficient. Okay, next the third possibilities. Okay, the third possibility, both they are different. Okay, that is a differential slope and intercept coefficients. Okay, we can have difference in slope as well as intercept by introducing both intercept and slope dummy variables in a regression equation. Okay, for example, here y is equal to beta 0 plus beta 1d plus beta 2 xd plus beta 3 x plus the other term. Okay, we have here intercept dummy and slope dummy or interaction term. Intercept dummy and slope dummy variable. Okay, when we estimate the estimated regression can be written as y hat plus beta hat 0 beta hat 1 d plus beta hat 2 x d plus beta hat 3 x. So if D is equal to 1, referring to male worker, okay, Y hat male is equal to expected value of Y given that D is equal to 1. Beta hat 0 plus beta hat 1 plus beta hat 2 x d plus beta hat 3 x p1 and 1. This is beta hat 0 plus beta hat 1 plus beta hat 2 x plus beta hat 3 x. Beta hat 0 plus beta hat 1 is the intercept. We can take out for x for the last two terms, beta hat 2 plus beta hat 3 x. So this is the intercept, and this is the slope. Okay, intercept, this is slope. Okay, next, if D is equal to 0, referring to female, Y hat female is equal to expected value of Y given that D is equal to 0, close the bracket, beta hat 0 plus beta hat 1, D here the value is 0, plus beta hat 2 x D the value is 0, plus beta hat 3 x. So this is beta hat 0, beta hat 1 times 0, it is 0, beta hat 2 x times 0, it is 0. What is left? Beta hat 3x. So the intercept is beta hat 0, the slope is beta hat 3. So we can see that intercept is different as well as slope also different. Okay, differential slopes and differential intercepts. And we can illustrate in a diagram. Okay, Y monthly salary and X the number of man hour. For male, the intercept is beta hat 0 plus beta hat 1, the intercept. The slope beta hat 2 plus beta hat 3, which is higher than beta hat 3, meaning that the regression line for male must be steeper. It must be steeper. Okay, the slope is beta hat 2 plus beta hat 3. Okay, Y hat for male is equal to beta hat 0 plus beta hat 1. This is the value of intercept plus beta hat 2 plus beta hat 3 x. Then for female, it will start with the lower intercept because the intercept here is beta hat 0 and the slope must be flatter. Lower intercept and flat. This is beta hat 0. the slope is beta hat 3. Ky for male is equal to beta hat 0 plus beta hat 3 x y hat. You can see that we have two parallel regression lines. Sorry, we have two not parallel regression lines, and with the different intercept. Okay, next is dummy variable track. Okay, what is a dummy variable trap? Is a condition where the independent variables are multi-collinear. Okay, multi-collinear means two variables are perfectly correlated. Two or more actually. Okay, next sentence is the definition of multi-collinear is the condition in which two or more categorical or dummy variables are perfectly correlated. For example, you have gender, male, male versus female. So if male is 1, automatically female is 0. If male is 0, automatically female is 1. It is perfectly correlated. Okay. For example, in a day, we have 24 hours. if you spend for working and leisure, if you work 20 hours, okay, your time for leisure is 4 hours. Okay, if you work for 2 hours, okay, your leisure or membuta is 24 hours, 22 hours. Okay, it is perfect relationship. Okay, perfectly correlated between working and leisure. This is multi-collinear. So how do we apply when it comes to regression with a dummy variable? For example, here a regression model with an intercept, meaning that the regression equation has the intercept value here, beta 0. For example, introduce dummy variable gender that has 3 categories. Okay, male, female, and transgender. Okay, there are 3. By right, we should introduce, based on the rule, we should introduce only 2 dummies. Okay, maybe on that day your brain is misalignment, you introduce 3 dummy variables. So when you introduce like this, okay, your dummy variable, male, female, and transgender, and this is your quantitative independent variable, this equation 3, will fall into dummy variable trap. Okay, dummy variable trap. Due to variable gender that has 3 categories and you introduce 3 dummy variables. Okay, this equation will fall into dummy variable trap. If you estimate equation 3, there is no estimation output. Okay, there is no estimation output. Estimating equation 3 will result in software error message. It means that the OLS doesn't work and you cannot get, okay, the estimation output. So how to overcome? One dummy variable must be dropped. In this case, okay, we must drop 1 and we have 2 dummy variables. You can drop either male, okay, or female or transgender. If you drop male, meaning that in your equation you have female and transgender. Because we follow the rules, for m categories of dummy variables, introduce only m minus 1 dummies. Okay, that's all for dummy variable chapter. And next week, we will proceed with chapter 8 in the book, in the topic of multi-collinearity. And this topic is interrelated with the assumption of OLS as well as the properties of OLS that we discussed just now: unbiased, minimal variance, linear, and consistent. Okay, any question? Okay, if there is no question, after this I will assign you one assignment on dummy variable, and please do some preparation or glance through the topic of multi-polarity so that it will make yourself easier to understand this topic. Okay, with that, see you next week, and Assalamualaikum.
Thank you, Doctor.
Right.
Thank you, Doctor.
Thank you, Doctor.